Good afternoon and welcome to Design Master Training. My name is David Robison. Today we are going to be looking at fault calculations in Design Master Electrical for Revit. If you are attending the training live, you can ask questions in the chat box. If you're watching the recording of the training, you can call or email your questions. Our phone number is 866-516-9497 and our email address is support@designmaster.biz. Today's topic, again, is fault calculations in Revit. So we'll be looking at how Design Master implements those for you, the settings that you need to get right in our software so that the fault calculations are coming in correctly. I've got on my screen here the default Design Master fault current schedule. You can get to this by going to DM Electrical, Schedules, and Fault. And this pulls up a schedule in Revit that's a standard Revit schedule. So there's nothing particularly special about this other than it's well formatted using our shared parameters. And it's giving us the output of the fault calculations. You can use this for your fault calculation output. You can modify this and make it look different. You don't have to use what we've presented here. It's a starting point. It's a standard Revit schedule. So you can use all of the values and the properties. We can go edit the fields, and we can modify the fields that are being displayed here and the columns. So you have complete control over what this looks like. A couple of things I do want to highlight. We have this panel tree sort order column. It's actually hidden. That's how we get this sort here on the left where it's got this tree. So they're not being sorted alphabetically. They're sorted based upon how they're connected to each other. So this column handles that sorting, and then that tree label is the label that has the indent in there. If you just want to do alphabetical labels, you can swap that out with the panel name from Revit. We have two columns for fault in the schedule. We have the fault at the device, and if that fault exceeds the AIC rating, you're going to get a warning. We also have the option to turn that warning off with a separate column. So we've got this fault without warnings. So if you include that, it won't have that the exclamation points. We don't have any AIC ratings set, so nothing's being shown as being out of compliance. If we just take something and we set an AIC value, so I'm going to go to the switchboard. I'm going to run a panel edit. In fault, we have the AIC rating. I'm going to set that at 30,000 amps. We run our calculation, and when we do that, it's going to check the calculated fault value against that AIC rating. And since the fault exceeds the AIC, we will get those exclamation points. So there you can see the exclamation points. So the default column is going to check the fault versus the AIC and can make sure that it doesn't exceed the AIC ratings. If it does, it'll put the exclamation points. If you don't want those, you have the option for the no warning column. That's the schedule. This is our output. This is all shared parameters, so you can do a different schedule. You can put this as labels on your plan view. You can do it as labels on the single line diagram, just using standard Revit functionality for getting these shared parameters being documented. So let's look at how these calculations work. The first thing you need to do is you need to set the starting fault. So we've got this service transformer, and it's got 65,000 amps. That is set in the panel edit command. So I'll run panel edit. We have our service transformer. We scroll down to the fault section, and this has been fixed at 65,000. If you have it calculated, we'll assume an infinite fault at the primary, and then we'll account for the transformer that it's going through. So you can do that, but generally speaking, you're given a value from the utility. They say, hey, we are going to provide, or you should design to 65,000 amps or whatever number they give you. And so you enter that number here. We also have a place for the XR ratio. If the utility provides that, you can enter it. If you're looking at a generator, you might have a fault with an XR ratio provided. If you don't have it, it's going to default to 5. That's typically going to kind of be within the range of what it probably is. But if you have more precise values, you can put that in. And then based upon that fault, we will calculate the fault in the rest of the project. So we're starting at 65,000 amps, and then everything downstream is being based upon that. The fault on the downstream devices is going to be based upon the feeder to them. So if we go take a look at the switchboard that's below that service transformer, if we look at the fault section, you can see that the fault is calculated, which is what you want. You don't want to have the downstream pieces have fixed values. This is actually what we're trying to do. We're trying to calculate those. So those are all going to be set to calculated. And then the feeder is going to be driving what that fault is based upon the impedances in that wire. So there's two pieces to the feeder of relevance. The first is the conductor size. So that's going to be set here. And then we also have the wire length. The wire length is set down here. The wire length has a lot of options for how we calculate that based upon straight lines, right angles, accounting for wire makeup. We did a previous training talking about the wire lengths. So if you have questions on how to set that, please refer back to that other training and you can see how we set those wire lengths. We did a whole training on that, just on the feeder lengths. Check that one out for the wire lengths. The other piece for the feeders is the impedance based upon the conductor size. So by default, we're sizing to a default size based upon the size of the panel. You can upsize that or change that. You can select a different value here. And that's going to correspond to a row in our wire ampacities table. And this is where those impedances are set. So if we go to customization and wire ampacities, this is where you have your X and your R value that are combined to figure out the impedance for the wire. So you need to make sure you get those values correct so that they're being used correctly in the fault calculations. These are being pulled from NEC table 9. If you scroll down to the larger feeders, we have multiple runs. The X and the R is still going to be the impedance values for a single run of wire, and then we'll do the math and we'll divide it by the number of runs. So you can pull these numbers straight from NEC table 9 based upon your wire size, and then put in the number of runs, and we'll do that, the math for the division. It makes it a little bit easier to enter the X and the R because it's coming straight from the NEC or whatever you have for what those values are. We also have the option to set a custom wire size. This will let you put in anything you want. The two common places that this would come into play would be if you have a bus duct or a bus gutter, you could specify, hey, this is a bus duct, and then you can specify the impedance values for it here because it's going to have a different impedance value. So you can have the label not be a wire call out. The other place would be if you have multiple parallel runs in a single conduit. We actually can't model that in Design Master. So you could do your wire call out here, accounting for that. And then you could put in the corresponding X and R values. And I believe there's some adjustments that you would need to make for that. But you can put the values in there, and then our software is going to do the calculation. So if you have a custom situation that doesn't fit kind of our standard feeder call out feeder system, you can use custom and you can put anything you want in there. So for the feeders, those are really the two pieces. It's the feeder size and then the feeder length that's going to impact these calculations. If we look at the transformer, we also have the transformer impedance and the transformer XR ratio. Those are going to be used in the fault calculation as well. So if you have those numbers from your manufacturer, you can provide them here. We have default values. The impedance is based upon the transformer size. So that does change a little bit as you change your transformer size if it's calculated. You can also specify the specific value. And then the XR ratio. Again, we're going to use 5 as our default. And if you have something more precise from your manufacturer, you can specify that. These values can be specified on each instance, and you can do it that way. So you don't need to make any changes to families. With our edit multiple, you can select multiple panels or multiple transformers, and you can make changes to multiple at a time. And that is fairly straightforward to do. You can also make these changes in the family itself. So if I select this transformer, I'm going to go highlight it on the model. So there's my transformer. We can run the Revit edit family command. And then in Design Master, we can run the family edit command. And here we can specify information at the family level for that transformer. So I'm going to change the device type to transformer. And now we can specify the size of the transformer and the impedance and the XR ratio, either for everything of that family or for each specific type. So this is how you could take your existing families that you have and get this information loaded into them from Design Master so that when you're using it on future projects, you've got these values specified ahead of time and you're not having to do that as a second step. We have to have this in Design Master kind of through our interface because Revit doesn't have a place to put any of this information. So we had to create a framework for storing all this information. So you have to use our command to get this information into your families, because Revit otherwise doesn't know about any of this stuff. But if you put it into your family, then you can use it in your projects. So far, we've been looking at feeders, which is connections to electrical equipment. We also calculate fault to your branch circuits. So if I pull up this here and we take a look at this piece of equipment, you can see that in the shared parameters, we do have the fault values being exported. So we have the fault, this cooling tower, being provided. It's also on the circuit itself. So if you look at the electrical circuit, we've also got the fault being displayed there. So we have this in the shared parameters in a couple different places, both on the feeders, electrical equipment, and on the branch circuit devices as well. If you take a look at this receptacle down here, the fault calculation does add a little bit of time to the calculation. So if we get a circuit that has a lot of devices on it, we don't calculate the fault. So if it only has a few devices, we calculate the fault. But if you get above 3 or 4, we just don't calculate the fault anymore, because it kind of doesn't make a whole lot of sense at that point, because fault is kind of a point at a specific value. And when you're looking at a branch circuit, the question would be, which one are you even looking at? So the fault calculations don't make as much sense on like a receptacle circuit. You wouldn't necessarily care about it anyway. But just be aware that it's not going to be calculated, but it is available for the larger pieces of equipment. We also feed the motor values in. So if you have a motor, that's going to contribute to your fault. So again, looking at this family, we have this connector. The connector has this toggle load subclassification motor. Not my favorite property name in Revit, but that's what they called it. If that's checked, that's how you specify to Revit that this is a motor. Design Master is going to honor that as well. That's what we use to see if a load is a motor or not. So if that's checked, we're going to assume that that load is a motor, and then we're going to treat it as such in the fault calculations and feed it back into the fault. Looking at the family edit for this device as well, if we change this to an equipment connection, we also have this motor multiplier and motor XR ratio, where you can change how we're going to do that fault calculation. By default, the fault from a motor is 4 times the load, and the XR ratio is 5. Again, those are kind of standard values that typically are going to work out. If you have something more specific, you can, at the family level, adjust that. So I'm going to go ahead and turn this on for this one, load this back into the project. If we look at our fault current schedule, right now we just have all of our fault from our utility. I'm going to turn on a couple of our motor columns as well. So there's the directly connected motor fault, and then the total motor fault. I just added that motor, so those haven't been calculated. I'll run the calculation, and it will add those motor values. It's going to show the values here, and then that value is going to be added to the fault at the device as well. So there's our fault from the motor being included, and you can see that it kind of ends up everywhere in the project, smaller values as it gets farther away. We include the fault from all motors. The standard typically is that you only want to include motors that are less than 50 horsepower. But the reason for that is because it's really tedious to model all of the motor faults. So all of the standards are essentially giving you an out to not have to do all that data entry. Since we're using Revit, and this is a building information model, you have all of that information. So rather than try and decide what the arbitrary cutoff is, I mean, it's 50 horsepower, but trying to, figure out, okay, this motor we're going to include and this motor we're not, we include all motors. So if you specify it as a motor, we're going to include it in the fault calculation, even if it's small. But since the software is, it's kind of built in, the small ones aren't going to matter that much. So it ends up not mattering, which is why you can kind of ignore them on other projects. But with our software, you're just going to get the fault from all of your motors, no matter what size they are. And just know that the small ones are not going to have much of an impact. The fault does end up fed back at the utility. And so there's always a question of how you handle this, because the utility gives you the fault. They say, hey, it's 65,000 amps. And the AIC rating on this transformer we're providing is also 65,000. Okay, then you add your motor loads, And even if you got a small motor load, it's going to come back and you're going to have a fault from that motor at the utility. And then suddenly you're over the 65,000 that they gave you. It's kind of assumed, there's an assumption in there that they're going to handle the motor loads coming back. And so they don't really, they give you that number assuming you're not going to feed your motor loads back into it. But our software does, because it's going to do that whole calculation. There's two ways you can handle this. If you just don't care about the motor loads at all, we have the fault that's just the utility fault. So you could use that value instead of the total fault. So if you use just the utility, put that one in there. That's going to give you just the utility fault, ignoring the motor loads. The other thing is, if you want to include those, what a lot of people end up doing is you go back to this panel, you say, okay, I've got my motor fault is 200. And so you do a little bit of math and you set this one to 64,800. And then you run your calculations. And if you do that math right, you're going to end up with the fault at that utility being the 65,000 when it includes the motor fault that was provided. That is everything I had to share with you about fault calculations today. So if there's any questions, you can go ahead and put those in the chat. I'm happy to answer questions about fault calculations or anything else related to Design Master Electrical for Revit. All right, there's a question. Can I talk about the fault with regard to automatic transfer switches and generators, where you've got two faults? We can do that. Let me put together a little example and let's just take a look at what our software does with it. So now we have the transfer switch being fed from the two separate panels. And the last thing I want to do is I do want to set the fault on this panel just so we have something. And we'll set the fault there as 10,000. Then we can go to our fault schedule and run the calculation again. Let's take a look at what that looks like. So the first part of getting the fault right for your automatic transfer switches is that you have to model it properly in Revit. If you don't know how to do that, we actually have a knowledge base article on how to do that, because setting up a transfer switch is a little bit tricky in Revit. So you get the transfer switch in there, you get it connected to two different pieces. Then you can see we have two basically source devices here, because that LP2 is not connected to anything. So it's essentially, it could act as a generator or whatever that's going to be. And since it's on the secondary, the ATS, it's not showing the things below it. So it's just kind of sitting here by itself. The ATS, we then have two fault values that are being shown. The first one is for feeder 1 and the second one is for feeder 2. So we show you both fault values, and we need one more piece in here. I'm going to put in one more panel and we'll run that calculation again. And then we can see what happens downstream of that transfer switch. And so here you can see that we have the fault at that panel downstream, but we're showing a single fault. What our software does is it takes the higher of the two fault values and continues the calculation on with that. So we have the fault from the utility, we have the fault from the generator, the utility fault is higher, so we carry on with that as the fault. We don't have a way to do a power study where we're looking at what happens with the whole system when just the generator is running. So there are some limitations here when you have an ATS as to the values that we can provide. So we're providing just the maximum rather than both downstream of it. If you really needed to have the calculation downstream, you'd essentially have to disconnect this ATS from the utility, run the calculation, see what the values are, write them out somewhere else, and then reconnect everything up. It's not ideal, but that's how our software can handle that calculation for you if you needed the fault on this downstream panel of the ATS in generator mode. Another question here, if the utility transformer is on a site plan in AutoCAD, where do you set the distance from the transformer to the MDP in Revit? You do need to have that transformer in Revit somewhere so that you can set your starting fault, essentially. So you need to have the transformer modeled as a transformer. It can kind of be off in space if you don't necessarily know where it is or it doesn't really fit on your model, but you do have to have it modeled as something. And then what you could do is you could run panel edit on that switchboard, the NDP, and you could set a custom length for the feeder length to that transformer, and that would be the way to set that length for yourself. But you do need to have the transformer inserted, because that's usually the starting point for your fault calculation. And so we do need to be able to set it there. We don't have any way to set the fault at like the upstream thing. So you need to have that upstream thing existing to set the fault. Thank you for watching today's Design Master training. Contact us with questions or comments by calling 866-516-9497 or emailing support@designmaster.biz.